but thank you. I'll record now. Sorry, I forgot to record, so let's take a step back. Tonight we're talking of the hypothesis testing, and the whole idea of hypothesis testing is to simplify results. And sometimes if you try and explain to somebody and you say, oh, the average is this and the average is that, or I've done regression analysis, they don't want to know that. What they would come back and say, just tell me, is it yes or no? Are we in control of the COVID virus? Yes or no? And sometimes it's very complex. But in terms of analytics, we can do what's called a hypothesis testing. So in this lecture, I'll give you the fundamental concepts and the steps that you need and how it all fits together, hopefully. And then we'll do a couple of examples. A good example to bear in mind, and sorry for those that have been in on the class, I'm repeating it, so pick me up if I miss something, is a criminal trial. It's a very good example to remember. And one of the things with our judiciary system is you are innocent till proven guilty. So the null hypothesis is always that somebody is innocent. And no amount of people looking at it say, ah, that guy definitely killed that man. It's on a piece of, it's on a film or whatever. No, they're innocent until proven guilty. Hope that makes sense. In a statistical thing, we want to do a test, and that's what we obviously will deal with. And it's often used in medical world. And I was telling everybody else, I've had to do the analysis for a headache tablet. And it's relatively complex. There was about 10,000 people, I think, from memory in the experiment. 5,000 of them got a placebo and 5,000 got a headache tablet. And they had to fill in forms of to what extent does this tablet make the headache die down or get less. There's 5 components. You have to state the null hypothesis. You have to state what is the alternative hypothesis. And then you have to decide on a test statistic. In our case, it will relate to the distribution of the statistic, and we'll have to draw conclusions from that. There'll be a rejection region. So if it's within a certain region, we will stick to our null hypothesis and say, yep, that's the null hypothesis. If it's outside of that region, we'll say, okay, now we accept the alternative hypothesis. That's always how it works. So there's a decision rule, and then what's not on here is conclusion, which is very important. Again, the criminal trial. How do we translate a criminal trial to the way we do statistics and business analytics? We define, if you look at this, the steps there, null hypothesis. In a criminal trial, the null hypothesis is the defendant is innocent. What's the alternative hypothesis? Just give me a moment. Okay, the alternative, if you look here, the next thing we need to do is have an alternative hypothesis. The alternative hypothesis is the defendant is guilty. The next step is we need to define a test statistic. In a criminal trial, how do they define that? Well, they put a whole bunch of people in a jury, if it's a jury trial. Does Australia? Yeah, Australia does have juries. Yeah. Um, um, so they basically get a group of people to decide whether somebody is innocent or guilty, isn't it? In the language of statistics, convicting the defendant is called rejecting the null hypothesis. In other words, if somebody is guilty, we're going to say we reject the null hypothesis that the defendant is innocent in favor of the alternative hypothesis that the defendant is guilty. That is, the jury is saying there is enough evidence to conclude that the defendant is guilty. So that's, I hope you understand how this works. It's sort of fascinating how the reasoning works. And it's interesting to me, and I think I mentioned it somewhere else, the kids in my wife's school, which is a primary school, they already talk of hypothesis testing, and they already understand the concepts about it. If the jury acquits, it is stating that there is not enough evidence to support the alternative hypothesis. In other words, the null hypothesis stay. In other words, the person is innocent. But note that the jury does not say he's innocent. They say there's not enough evidence for the alternative. And that is true. That there's never a judge that says you're innocent. He says not guilty. That's what the judge would say. Okay. Now you can understand that, again, if we look at the trial, there's two types of mistakes that can be made. Somebody might be innocent, and by hook or crook they are found guilty. Do any one of you know of a court case that worked like that, where somebody that was innocent, but they were actually found guilty?
Maybe in movies.
There's actually a very famous case in Australia. Can anyone think of one where somebody was innocent, but they were actually found guilty?
Are you talking about that dingo case?
Yes, that's the one I was thinking. Yeah.
What was that one?
There was, yeah. Do you want to tell Shama?
I learned about it in school, but apparently there was like a family, and they were like their daughter was they were it was believed that they murdered the daughter or something like that, but
yeah,
really it was the dingoes.
They were camping, and the next day the daughter was the body. Well, I think they never found the body. I'm not sure whether they found the body, but they found clothes that was full of blood and so on, not far from where they camped. And they said a dingo pulled her away and killed her. But for whatever reason, the court decided no, they killed her. They killed her.
Whoa.
But years and years, I don't know, 15 or 20 years later, they did DNA testing, and they found that, yep, it was in fact a dingo that killed the girl. And the woman was let out of jail. She was in jail all that time.
My gosh.
Innocent, yeah. So it does happen. But I think on the other side, do you know of anyone that's guilty that was actually found innocent and or was found not guilty and is now roaming the streets? And okay, overall, the court does not worry too much about that case. They just don't want an innocent person in jail. Just imagine if it happens to you. You walk down the street, and the next moment the police catch you and put you in jail, and you go to court and they say you've killed this girl somewhere, or you've done something completely wrong. I'm innocent. And they say, what's your alibi? And you say, I haven't got one. I was just alone at home. No, you were not alone at home. You were at her house and you killed her. and you are completely innocent, but now you're in jail, and that's just tough. So the court really don't want to make that mistake, in particular in the case of corporate punishment where they hang somebody or kill them. Just imagine, and there's been cases where someone was hanged and then later on someone else confessed and say, no, I was actually the criminal that did it. Anyway, long story short, so if the null hypothesis, i.e. this innocent, is true, and you do not reject the null hypothesis, that was the correct decision. And if the null hypothesis is false, i.e. somebody is guilty, and you then reject the null hypothesis, that's the correct decision. But there's a type 1 error and the type 2 error. And you can stipulate what probability, which is this alpha, for each of these types of errors you want to make. And if alpha, you can make alpha small, but then beta is big, or you can make beta small, but then alpha is big. So by playing around with this alpha and beta, you can say, what kind of mistake are you willing to make? And we're sitting with COVID virus. We can have a policy of do nothing, which means a lot of people will die or potentially die. We don't know. Maybe a lot of people will die. Or we can say we're going to kill the economy and so on, and hopefully save a lot of people. But nobody knows what the real right decision is, isn't it? We'll only probably know 20 years from now, and even then it will be difficult to say. I want you to make sure that you know this picture. Find memory hooks of how you can remember this very clearly, that there's two types of errors that you can be in. Two types of errors, and there's two situations where it can be correct. And my own memory hook, what's my own memory hook? My own memory hook is that of a court case where H0 is the person is innocent, and I do not reject that the person is innocent. That's the correct decision. If on the other hand they're innocent and I accept that they, or I reject it, if they're innocent and I reject it, that's type 1 error. On the other hand, if they guilty or they're not innocent, then I want to reject the fact that they're innocent. Okay, I don't know. Just remember this picture. Okay, type 1 and type 2 errors. I've explained what I think you should know about it, which is that picture. Just remember the picture. And I've said to you that you can define the probability of making a decision, and the probability, and it's an alpha and a beta. So type 1 error, where somebody is, okay, let me go and see. Where somebody is innocent and I reject it. So that's type 1 error. In our judicial system, they make this alpha small, something like 0.05 or 5%. So if there's 100 court cases, they'll only 5 times make somebody go to jail that's actually innocent. So typically setting for alpha is 5%. And that, does it remind you of the previous work that we've done? It's related to that. We arrange to make alpha small by requiring a prosecution to prove its case in instruction beyond reasonable doubt. That reasonable doubt is 5%. Or in our statistical world, it's 5%. Null and alternative, there are two hypotheses, the null hypothesis and the alternative. I think I've stressed that now. Okay, so let's look at it. What does it look in statistical term and terminology? The one that we're going to focus on is population means. How do we test for the average? So the null hypothesis is there's no difference. In other words, the population average is the same as the sample average, or is the same as a given value. The alternative is they're not the same. The sample or the population differs from that value. And how are we going to test it? We're going to take a sample of 100 or 200 or 300, measure the average or calculate the average, and then decide using our normal distribution or t-distribution type technique whether we're going to reject it or not. Again, there's one example where if the variance is known, we're not really going to focus on that because the variance is mostly unknown. If the variance was known, we could have used a normal distribution. Because the variance is unknown, we're going to use a t-distribution. Simple. Okay. Take note of population proportions, but we're not really going to look at that. Okay, concept. The rejection region of a test consists of all the values a test statistic for which H0 is rejected. An acceptance region is where H0 is not rejected. The critical value is the value that separates the acceptance and the rejection region. We'll see a drawing just now. The decision rule defines the range of the values of the test statistic for which H0 is rejected. Okay. So, in summary, there's two hypotheses, a null hypothesis and an alternative. The procedure begins with the assumption that the null hypothesis is true. You always start with somebody is innocent. The goal is to determine whether there's enough evidence to infer that the alternative hypothesis is true. There are two possible decisions. There's enough evidence to support the alternative evidence or hypothesis, or there's not enough evidence. Try and put this in your memory as well. Enough evidence, not enough evidence. Okay? Enough evidence. And it's always about the alternative hypothesis that you're looking for evidence. And there's two types of errors, and we've talked about that. And can you see that this is the 5 steps? Set up the two alternatives, design a procedure that under the assumption that the null hypothesis is true, calculate the test statistic, make a decision, and bear in mind there's two types of errors. Consider an example where we want to know whether a population mean is different from 130 units. In other words, what is there? Maybe you buy a chocolate that's 130 grams. And we now want to know if I test 100 chocolates, is the average weight of them 130, or are they not 130? Obviously, if they weigh more, I'm losing money because I put too much content in it. If it's way less, my customers will complain to me. And I've worked for a company called Frosty Boy. They make ice cream on exactly this problem. The testing procedure begins with the assumption that the null hypothesis is true. So we start with that is true. And the goal whether there is enough evidence. Okay, so then there are two possible decisions that can be made. There is enough evidence or is not enough evidence. We do not say, and here again, we do not say that you accept the null hypothesis. You never say that. You always reject the alternative, which means you accept, but you don't say it. It's interesting. If the test statistics value is inconsistent with the null hypothesis, we reject the null hypothesis and infer that the alternative hypothesis is true. Okay, I'm going to go through this just so that we can get an example, or not through this one, the next one. I'll go through the next one. Okay. Say there's some production and it takes 130 seconds to make something. We draw a sample of 100 and the sample mean is 126.8 seconds. If the process time is normally distributed with a standard deviation of that, can we conclude that the belief regarding the mean is incorrect? Now, don't worry about the calculations. As you know, by now know, we in the end going to end up using Excel. So, but try and understand the concept. We start off data type, numerical, single population, and delta is known, or the variation is known. To test the hypothesis that the population mean mu is the mean different to 130. Hypothesis 0 is mu is the parameter of the population, right? And the alternative is that it's not 130. So we calculate the test statistic, so don't worry too much about it. Level of significance alpha 0.05. You'll see where we're going to use that in Excel. And in this particular case, take note, we're interested if the time that it takes, this 130 seconds, is not equal when it's not equal to 130. That means it's called a two-tailed test, and you'll see now why. Okay, so now we have to establish a rule. The rule is if we calculate the average for this 100 and it falls within this area, we're going to accept the null hypothesis, which means it doesn't differ. Can you see that? If it's outside this area, and this is where we bring in the statistics, we're going to reject it.
So if it's outside, the more unlikeliness it's supposed to happen. So we judge it by the middle.
Yeah. If it's outside, it means that that value is way different from 130.
Mm.
So I again encourage you guys, whenever you get this type of problem, draw this drawing, and you'll see me do it plenty of times now. Okay, so if your alpha is 5%, there 0.05. If it's what's called a two-tail, this one is 0.025 and this one is 0.025. And then we do a whole bunch of calculations, which we will do in Excel just now. And we calculate the test statistic, and we say, in this particular case, our sample average was 126.8. Can you see that? So now, Mike, if you look at 126, sits about here. Just with your eye, do you think we should reject it? No, because it's in this region. So let's see what conclusion. Okay, it says minus 1.2, minus 2.13. Okay, sorry, it sits here. Minus 2. If you look here, minus 2.13. If you do this calculation, minus 2.13 sits here. So yes, we want to reject it. This differ too far from that 130. Okay. We'll work through an example and hopefully you'll understand. The p-value of a test is the minimum level of significance. P-value is the probability. So the probability, what's the probability that we got that result given all the assumptions that we've made? In this particular case, the probability is 0.03, which is less than the alpha value of 0.05. Again, based on this, we can say we're going to reject it now. Okay. I think you guys, my eyes are glazing over, so I'm sure your eyes are glazing over. And yes, let's get into a real example.
Quick question. This is the same question I had to my another unit, is that a lot of the stuff that we learn each week is about 2 to 3 hours long, and the exam is 2 hours. So obviously you guys can't exam us for everything.
Yeah.
Will we get a heads up a little bit of like what sort of things?
Nick, that's a good question, and I have pretty consistently, in my humble view, each chapter that we do pinpointed exactly
Oh,
what
yes.
areas we're looking at. So, and I then made the point that consider the rest as background, and sometimes you need to understand this part to understand the next part.
Yeah.
And my focus is very strongly on, can you do it? So I hope that answers it.
Yeah.
So if you look now, what we've done up to now is we looked at 12.1, concepts of hypothesis testing. And I would say we skipped through 12.2 because I kept on saying to you, don't worry about this. We're not going to do this calculation. And we looked a little bit at 12.3, the p-value of a test. And again, it will become clear when we do an actual example. I have to admit, just before you guys came on, I already did an hour for BUS204. So I'd like us to take a 5-minute break now, and then I'll start working on this particular example. Is that okay? See you in 5 minutes. Okay, I'm not going to do this one because we seldom. Okay. If we reject, then are you guys back? Yeah, yeah. Linda, are you here? Sharma is back. Who else is there? Tariet. Okay. So XM1202. There are a variety of government agencies devoted to ensuring that food producers package their products in such a way that the weight or volume of the contents listed on the label is correct. Recently, a number of customers complaints were received regarding the weight of the garlic packs imported from overseas. So let's see if that example is here. Okay, I'm going to see if there's a T distribution example. Okay, I'm going to start with example 12.5. If you look in your book, now I haven't done this, so you're going to discover with me how to do it. How cool is that, huh?
Did you say 12.5 example or?
XM05, it's on page 496.
Okay.
And I'm going to bring up the data. Give me a moment.
Is it the one and it says production?
A manufacturer of television screens has a production line that used to produce an average of 100 screens per day. That's the one. You got it? XM 12.05. I just want to close this other one. Man, have I got stuff open here? Okay, no, I'll leave it open for the moment. Okay, there's the production. So can you remember the steps? Step 1. Determine the null hypothesis. Okay. What is the null hypothesis? The null hypothesis is mu equals 100. Okay. A manufacturer of television screens has a production line that used to produce an average of 100 screens per day. Because of recently introduced government regulation, a new safety device is installed, which the manufacturer believes will reduce the average daily output. After installation of the safety device, a random sample of 15 days production was recorded, and that's what we've got there. So the alternative hypothesis, let me just see how do you spell hypothesis.
Hypothesis.
I think I got it right now. Is MUH is, in this particular case, it's actually less than 100. Because they think, yeah. Sometimes it's easier to first define the alternative hypothesis. In other words, yeah, at any rate, that's it. Okay, so we don't have to worry too much about the rest. So let's see if I can do this analysis. Sometimes, and I'm not sure if this is true, I'm going to add a dummy here. So I know the thing I want to test against is 100. So I added the dummy variable. This is quite important, by the way. And then I go to data, and I go to data analysis, and I go and do t-test, because the variation is unknown in this particular case. And to sample test, assuming unequal variances. Okay, so the variable range of 1 is this one. The variable range for range 2 is this one. The labels, I've got a label, and did they specify 0.05%? Let's see. Yeah, use alpha equals 0.05. So 0.05. I want to output it on this spreadsheet so I can see what's happening. And let's just see what we're going to get. Output range missing. Okay. That's what I wanted to specify, man. There. Click on OK. And voila, Bob's my uncle. Except for a few problems. It doesn't want to calculate. Okay, I'll do a dummy like that. Let's see if it works now. Data analysis. Click on OK. Mean difference. Hypothesized mean difference. Okay, we hypothesize that the difference is 0. Okay. There we've done the calculation. So let's just understand what we've done here. This dummy is the expected value is 100, isn't it? So I draw a sample of 15, and I got an average of 96. So at least I feel, yep, it is less. Do you understand that? If it was in fact more, we can stop the thing right now. If this average turned out to be more, we don't have to do anything more. We know we can reject it. Okay. But let me draw my drawing that I always draw, because I draw drawings. I can't stress this enough that you have to do this.
Can you just after you finish drawing, can you just like explain the drawing once more? Because in my exam quiz, I did the drawing just because I know you liked it. So then I hope to get bonus marks.
Yeah. Okay, I will. Okay. So under the null hypothesis, we know that this value here is 100. If you read in the book, produce an average of 100 screens per day. That was the null hypothesis. Do you see where I got that from? And I now know that using this, the calculations here, the variance, by the way, the standard deviation, which you need to calculate, is the square root of the variance. And I know, and you should know, roughly 3 standard deviations should be right at the end here. So that equals 100 plus 3 times the standard deviation should be this point here. And this should be equal 100 minus 3 times the standard deviation. So I now know where what the graph looks like. Now I want to draw where the result that I got was 96. And 96.46. 96.46. So that's the result that I got. Now I need to draw in. So for starters, yes, it's less than the 100 that it used to be, but is it less enough? And you can see if this line is actually sitting here, you can immediately say, oh, no questions asked, it's less than 100. Hypothesis, it's less, mu is less than 100. I reject the null hypothesis. Can you see that? If this value, however, sits here, well, it depends, isn't it? I now need to calculate where is this 5%? Where does this 5% sit? Does that make sense, Nick? Do you need me to go through it again?
No, that is good.
So under the null hypothesis, we know that the t distribution would look something like this. Under the null hypothesis. So if I now get a result that's outside, very far away from there, I go, the null hypothesis, it can't have happened under the null hypothesis. The probability that this happened under the null hypothesis is too small. So I can immediately go and look, for instance, at this P one tail. For starters, let's just ask, this is a one tail. Can you see that this is a one tail because it's less than 100? Nobody cares whether it's more than 100. We only want to know when it's less than 100. So that's why it's a one tail. Okay, it's an important distinction. So I don't care if this value was sitting here. I don't care about that. I just want to know when it's, my hypothesis says, my alternative hypothesis says it's less than a 100. Now I can immediately look here under the probability. The probability that I got this result, can you see there, is 0.6%. If I turn this into a percentage, it's points. Oh man, no, let's not do that. Control Z. Okay. The probability is definitely less than 0.05. Can you see that? So I already know that getting this result, 96.5. Okay, let's just work through the calculations. Okay. Okay. So the thing that we want to look at is this t-stat, and the other one we want to look at is, so this value We want to compare this value with this value. Okay. And if this value is less than this value, but this one you need to put a minus sign before because it's on the left-hand side of this value here. So is this t less than minus this? So equal
Yes.
minus 1 times this. If this is less than that, then I want to reject it. So I reject the null hypothesis and I say, no, 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 it's not equal 100, it's less than 100. I accept the alternative hypothesis. I have to admit graphically this doesn't look right to me, but I have to live with what the answers is of the evidence. Yeah. Okay, so in this, based on these calculations, I'm going to reject the null hypothesis because this one is less than minus this one. This, and you always need to do this calculation. And again, with a drawing, you can see that the t value will should be a minus because it's on, once you've, yeah, if it's on this side, it needs to be negative. So I have to admit, it doesn't look, still doesn't look right to me, but that's the way it is.
Francis, could you please say the equation you did for that again with the t stat and the t critical ones up?
Yeah. If you look on page 497, you're comparing the t stat value, and if it's less than the t critical one tail, and in this particular case we've got to multiply it by -1. If it's less, reject. Bottom line, reject. On page 497, you'll see that those values are there. 2.82 is less than -1.76. And the answer is this. Let me see if I can work it backwards, if I can actually get to the value. Times, let me just see. If you look there, this, yeah, okay. You remember what, if we call something called normalized, now it's slightly different with the t statistic. We want to end up with this being 0, and I want to end up with this being 3, and I want to end up with this being -3. That's when you normalize, and that brings you to this type of statistic. So -2.8 will be here somewhere. So this line is correctly probably more towards this side, more -2.8. If I look at my values here. The truth is, I sort of know it verbatim. The test is this is less than that. So this one, so 1, and this is 2. And if 1 is less than 2, then I reject. Okay, that's in the first place. The other question is this probability, and we're in a one-tail situation. Okay, say 3. If if 3 is less than whatever my, in this particular case, alpha was 0.05, less than alpha. Reject. So there's two ways you can check whether you want to reject. This probability, I personally actually like this one more. Why? Because it's sort of easy for me to understand. The probability of getting this result when this null hypothesis is true is very small. It's 0.006. Can you guys understand that kind of thing? So Excel is doing all these calculations for us, so I don't really need to know more in terms of making it a practical application. I think what is interesting is, and what they do in the book as well, and it's a good test, is to do an actual histogram of this data. Shall I do that quickly? Pivot table, yeah, just in worksheet. You know how to do a pivot table by now, hopefully. Drag production there, drag production there. Make this a count. Group this. I'll arbitrarily group it by 5. Click on OK. Yep, insert my famous graph.
So pretty much a hypothesis test is for us to create a conclusion, and a conclusion is like a one-sentence information for any person to look, be like, okay, I know what this means.
Yeah. Well, you basically will say there's not enough evidence to, we keep the null hypothesis, or we reject the null, or we adopt the alternative hypothesis. Yeah. So it's, you're right to give one simple answer. So the simple answer here is no, the time it takes to produce this is now less than it used to be. Used to be 100 seconds or 100 minutes or 100 whatever.
Yeah, so it has decreased.
100 screens, sorry, producing 100 screens per day. We're now producing less screens per day. So it's actually a bad result in this case.
Yeah, because it's decreased, right?
Yeah. So, and here you can see, can I get this result if I actually expected it? If it was really around 100, you can see that the mode and the average and the mean should have been here. But you can just see on the graph, no, it's all towards the left. Okay, so again, this graph is helpful to do and see if that's still in line with what your thinking is. Okay, let's see if, okay, in all of this, what is more important and what I can almost tell you now is in some exam somewhere, is where you have to specify the steps and then go through an actual example of steps. Okay, so, and we're not going to deal with where the variance is known. We always deal, all the examples or all the exam questions will be where the variance is unknown. You've got that? So, Z. Okay. This is the exact example that we've done. So let's work through it. Data type numerical, single population. So how do you know which test to do? Well, it's numerical. So does it work for nominal data? Can I do this for nominal data? No, it's got to be numerical. Am I dealing with one population? Yes, one population. In my particular case, is delta known? No. So most cases, in all the cases that you'll deal with, this is unknown. Population variance is unknown. So I'm going to use the standard deviation, which I calculate from my sample. I don't know why it says the variation known. It's actually variation unknown. Can you see that? I won't fix it now. We investigated the mean. We assume normality. Can we check for normality? Yes, I can draw a histogram and see that it's sort of normal. Okay, so that's identify the technique. Hypothesis. Me equals 100, which is the average for the population is 100. The alternative is I produce less televisions. I produce less than 100. And it's a left one-tailed test. The test statistic, you can look at it, but that's the thing that we calculate, that T that we get in Excel, that we calculate. Let me go and bring it back up. This T stat is what Excel calculates for us. So I do not need to know much more about the formula than this. The level of significance I've got to specify. The critical value is minus T. If the reject H0 if T is less than minus 1.6761, otherwise do not. So let's go and look at my example. Yeah, there's the critical value. If this is less than minus that, then I want to reject it. So you only need to compare this one with this one. Value that, so they've done some calculation. They come up with minus 2.82 as the T statistic. There it is, minus 2.82. And T is less than that. Reject H0. There's enough evidence to conclude that the mean daily production has decreased. So since they installed this extra device from the government, they produce less televisions. Well, that's sort of really it in a nutshell. And then there's the probability method, where you say the probability of this happening is 0.0068. And since P is less than alpha, 0.05, we reject HO. So there's two ways of doing that rejection. One is if the T value is less than the critical value, or if the P value is less than the alpha value. Okay, interpreting the results, the manufacturer would be advised to look for ways to restore productivity with the safety device in place. Perhaps developing another safety device would help. We note that the results are valid only if the assumptions that daily output is normally distributed is true. And that's important whenever you produce any report from now on. You need to draw a conclusion and draw an interpretation. Okay? And here's how you can do it in Excel. I'm not sure if, yeah, this t-test mean, they've removed it. So the trick that you and me now have to do is we add this dummy variable. Okay? We add this dummy variable, and then you go through the t-test for two means. Two sample assuming unequal variance, that one. Clear as daylight, I hope. Let's see if there's another example. So that's the result that you and me got as well. Alternative is the sample mean, sample standard deviation are already known or calculated. You can use this is the t-test mean worksheet. Checking the required condition, we need to check that it's normal. So draw a histogram, check that it's normal. As discussed, we make two, okay. Now we want to look at the probability of a type 2 error. Now the type 2 error is beta, and beta is 1 minus alpha. So they're always in contradiction with each other. Let's see if there's another good example. Okay. Do you want me to do another exercise? 12.38 in the book?
Yeah, the 12.38 one will be helpful.
12.38, okay. I've clearly not done it before, so let's see. And I don't really know the answer, so we'll have to make sure we get the right answer, isn't it? Okay, 12.38.
Because that would be analyzing t-tests of the mean, right? It's.
Sorry, I'm not entirely sure what you asked, Nick. Just try again.
We are going to, with the example 12.38, is that calculating the population?
Yeah. Okay. So let's just work through the steps. What is my null hypothesis?
Your null hypothesis is less than 7, so 7.
Okay. Well, I thought it's my null hypothesis is equal 7.
Equal 7.
You always try and get it equal 7. Okay.
Okay.
To an equal value. And my alternative. Alternative hypothesis is me is greater than 7. Okay. So now I want to do my test. Okay. What do I do? I'll write here, add dummy variable. Add a dummy variable. So we make equal to the value that we expect it to be. And you don't need to make it the full length, but I always do. It just makes it simple for me.
Yeah, it's just so it helps with that calculation.
They've removed that particular function for some odd reason where you only have to have one, you now always have to have two. You can see there's not a t-test for one. There's only one for two. So does that make sense? Not really, but anyway. Okay, so X is that. The dummy is that one. Okay, is it 0.05? Oh no, they want it at 0.10, so that's 0.1. Okay, output range is there. Yeah, that's good enough. Hypothesize mean difference. Yeah, we expect the average of this to be, okay, click on OK. There it is. Now, first of all, is this one bigger than that? Yes, it is. And how much bigger is it? It's just a good thing to know. It's 1.9 bigger, okay? So if I draw my famous thing that I always draw, and I encourage you guys to draw. Okay. Now, under the null hypothesis, this will be 7. This should be a 7. Okay. The variance, and I can calculate here the standard deviation. I'm surprised that they don't give that to you straight away, but here, square root of variance 3.13. So 7 plus 9, 16. This will be roughly about 16, which is 7 plus 3 times 3. This is just to give me a rough indication. And 7 minus 9, this will give me minus 2. Roughly minus 2. Okay. What was the actual result that I got is 8.9. And that's 16. 8.9 will be something sitting here. Would you agree? Roughly 8.9. So that already gives me a feel that possibly I'm not going to reject it. Now I look at the P statistic. Under alpha equals 0.1, this is actually smaller than 0.1. So I will.
Why is it? What? Sorry, why is it 8.9? Should it be 8.8?
The mean is 8.9.
Oh, yes, yes.
Should it be 8.8?
Oh no. I was thinking something different. I was thinking 7 plus T stat.
No, this 16 is 7 plus 3 times 3, because the standard deviation is 3.
Yep.
Okay. So I already know that I want to reject it on alpha 10. Okay. And now the T stat, I can also see that in this particular case, because I'm dealing with a positive side the whole time, I can see that the T stat is bigger than the critical one tail. The critical 1.38 will be here somewhere, but this is bigger. T-stat bigger, that greater than T. In this particular case, it's again a T critical one tail. So in this particular case, I've drawn the conclusion that this is bigger than that on a alpha of 0.1. Another way to put this is I'm 90% certain that this is bigger than that one. 90% certain that 8.9 is bigger than 7, considering the variation that's in here. Again, I can draw a quick histogram. I don't know how good or bad it will be, but let's see. I hope drawing a histogram is second nature for you guys now as well, not just for me.
I dream about histogram.
Yeah. And group it. Group. Make it 3. Yeah. Insert histogram. Yeah, it's very few points, but it's as good a normal as you can get, I guess. Yeah, I would, well, obviously, given how small the population is, I'll draw the conclusion that it's normally distributed. Okay, let's do 12.51. Shall I give you, I'll give you 5 minutes to look at 12.51, and then I'll go through it. Brenda, Target, are you still awake?
I'm still here.
Okay. Can you try and do 12.51? I'll
Sure.
give you
Yep.
5 minutes, and I'll be back in 5 minutes, and then I'll go through it.
All right.
Fair enough? Okay. Right. How did you guys do? Managed to do it. Chop, chop.
Still going, just 2 seconds.
It's XR 1251.
Yep.
I'll bring it in so long.
Has anyone done it? I need help. Ayo, Natana, have you done it?
I'm still going.
Yeah, me too. Me too.
Well, I missed that. Are you still busy working on it?
Yeah, I'm just stuck.
Okay.
Just trying to remember how to do it.
How do you calculate the alpha again? Sorry, Francois?
It's given to you. If you look there,
Oh.
in this particular case, it's 10%. So it's not calculated, it's given to you. But if the boss asks you to choose one, choose 5 or 10. Doesn't really matter.
So the alpha is always given to you.
If any one of you want to share your screen, then I'll talk you through how would you like that.
Yeah, I could do that. I can do that right now. So I was just about to get the standard deviation.
the conclusion in line 29 is it's a one-sided test, isn't it?
Yeah.
Which means it's a one-tail test. So you need to do one-tail statistics.
Yeah. I'm just trying to draw that graph that you mentioned before.
Okay.
Oops.
What I normally do is I just cut and paste that other line and then turn it. But anyway,
Oh,
there you are.
okay. Well, that means then here, would that be the mean there?
Yeah, which is 20.
20, yes. And then 22.6 somewhere up here, right?
Why?
Because here, variable one, no?
No, it's 20 plus 3 times 3.41. 3 standard deviations.
Oh, yes. So it equals,
Times 3.
times 3.
Yeah. You can go and read about the theory about it. It's 3 standard deviations. Really?
Well, no, I think I just didn't bracket it. That's why, hang on.
No, it's plus 20 plus.
Oh, yes.
Okay. And on the left-hand side, it will be roughly 10.
Yep. Because it's just minus, right?
Yeah.
Yep.
Okay.
And from here, because we know it's one tail,
Yeah.
we use this one, right?
No, then lower one, that one, 1.317.
Yep.
And so the T stat needs to be bigger than the T critical, which it is.
Yes, it is.
So what are you going to do? So you're going to reject the null hypothesis.
Reject the null hypothesis because it's bigger, right? Because it's meant to be smaller if it is the null hypothesis.
And the p-value, you can also see from the p-value, it's 0.00, which is way smaller than the 0.1, which is the alpha that they've given in this particular case.
Yeah, the alpha is the 10%.
Yeah.
Yeah.
So it's 0.1, but the pt1 tail
Yep. Yep.
at 0.0004 is less than 0.01. Okay.
So in conclusion, Is that enough wording for me, or do I have to say more stuff?
I'm just checking here. You can use those words. We can infer at 10% significance level that the population mean is greater than 20.
We can infer the
That,
population
yeah.
is decreasing, or shall I say is greater than 20?
Yeah, it's greater than 20. No, is greater than 20. And you can see it there in your calculations. It's 22.6, which is greater than 20.
Oh yes, it's greater than 20.
Okay, I think you've got it.
Oh, just like that?
Well, can you do it in an exam? That's the question.
Oh, I'll just have to practice after today to make sense and watch over this video.
And the 8 steps is the important thing. So, or 6 steps. So if you write out those 6 steps, make sure you write it out. Step 1, step 2, step 3. The null hypothesis, the alternative hypothesis, the test that I'm going to do, the result of the test, and the conclusion.
Oh, okay. The 6 steps are very important.
Yeah. I think okay.
Yeah. And what part B says, what is a required condition of the techniques used in part A? Use a graphical technique to check that required condition. Is that the one I just did?
That's the histogram.
Oh, yes.
To do the histogram.
Yeah.
Do you want to do it quickly? Share your screen, do it.
Yeah. All right. Should I group them?
Yes, group them. Group of 3.
Do I need to round down and round up for this one?
Yeah, okay. Yeah. Okay, here's a case where you can see it's not, one can argue it's not normally distributed.
Yep.
But on the other hand, if you look at the p-value, it's much smaller than 10%. So even though it's not as normally distributed as one would like, I would still stick to the hypothesis or rejecting the hypothesis.
Yeah, because this graph doesn't show it as well.
Yeah. Okay. Okay. Shall we take a 5-minute break and then we're back?
Can I ask a quick question again?
Sure, you can have a slow one too.
Yeah. How do you what's the two numbers that you use to get the two values on the side of the of the main.
That's 3 times the standard deviation. Is that what you're talking about? On the little picture that we draw?
Yeah.
Yeah, 3 times the standard deviation. If you want to go and review, it's under the normal distribution. Continuous, it's chapter 8. Okay, I'll look it up for you somewhere, but it's 3 times the standard deviation. Okay, let's take a 5-minute break and then we'll be back because you guys have been working now while I took a break. So I don't want to be unfair to you. Okay, see you in 5 minutes. Okay, we will take the 5 minutes. Okay. You threw the worst.
And I just want to touch base. You know how you said to find the other value, it's the 3 times the standard deviation for the one on the right. And then the one on the left, would that be the mean minus the standard deviation?
3 times. And you can look on page 151. It says they're interpreting the standard deviation, and it comes up with something called empirical rule. Approximately 68 of all observations fall within 1 standard deviation. 95 of all observations fall within 2 standard deviations, and 99.7% of all observations fall within 3 standard deviations. So that's where I got it from. So if you draw your curve, your normal curve like this, the 2 points will be 3 times standard, the mean plus 3 times standard deviation, and the mean minus 3 times standard deviation will be the endpoints.
The mean plus 3 times standard deviation.
And yeah, look on page 151. And if you can conceptualize and really understand that and bury it in your brain somewhere, it will stand you in good stead. So if the boss comes to you and say, I want an estimation and I want to be 95% sure, you say, oh, plus or minus 3 standard deviations. If he says, I just want to be 70% sure, you say, oh, plus or minus 1 standard deviation. Okay, Google, stop. Okay, let's see what the rest of the slides is. I think we nailed it. So. Okay, checking the required condition, draw a histogram and see that it's sort of normal. Calculating the probability of a type 2 error. So we know that type 1 error is alpha because that's what we defined. But what about type 2 error, which is beta? It's important that we understand the relationship between the two. And the relationship is, okay. Consider the following hypothesis test given the information there and determine beta, type 2 error, when mu is 180. So you can work the opposite way around. You start off with alpha equals 0.05. The decision rule in terms of Z would be, and then they do all these calculations. Okay, I'm not going to go through this particular example. The bottom line is beta is 1 minus alpha. I hope that's what they come to. Effects on beta of changing alpha. Change alpha to 0.01. The decision rule becomes that. Okay, I'm not going to focus on this much. You guys can go and read it. Judging the tested statistical test is effectively defined by the significance level, alpha, and the sample size, both of which are selected by the statistician as a practitioner. Therefore, if the probability of a type 2 error is judged to be too large, we can reduce it by increasing alpha or decreasing the sample size. Okay, you don't have to worry about it too much. It's sort of interesting to take note. Okay, I think what is interesting is here, power of a test. No, judging. Okay, proportion is using the same type of technique. Again, read through it, take note. It's not what we're focusing on. So I'm not going to go through any of these examples with you. You feel free to do it if you want to. Okay, and we can also do a hypothesis testing about P. So okay, what technique should we use? The first two is the type of data. The problem objective is to describe or compare two populations, and we've done that. We've done describe a population, we've done compare two populations. We analyze the relationship between two variables. We're going to focus on that next week again. And here's a summary. If it's numerical, this is the type of stuff that you can do. We only went through the t-test of me. If it's nominal, we can do a proportion test. We didn't do any of that. So you're only really interested in this one here. And that is it for a single population. So if we have a hypothesis about a single population, it's always, in our case, about the average. And we always want to make a statement about the average. The average is higher now or lower now, or the average score for students in this school is higher than in that school. We want to make some comparison between the two, and that comes up with a hypothesis test that we want to do. Any particular questions? Okay, I'm going to release the assignment effectively tonight, now in front of your eyes. How do you like that?
Yeah. For the exam, do you know roughly of how many multiple choice questions comparing to like Excel stuff?
I think it's about half the marks is, why don't you like, do you like them or don't you like them?
I prefer doing Excel.
Okay.
Yeah, same.
Yeah. I'll go and look at the exam and let you know. Not now, and I'll put something in the news forum. It will be good if you, in the discussion, ask the question and say, can you give us more indication of what the exam looked like? And then I'll answer it. How's that for a plan? Okay, I'll bring up the assignment and show it to you guys now and give you a bit of a discussion about it. Okay, so I've stepped away from using the coronavirus. To be honest, it's just too complex for the scope of this particular thing. So okay, I'm going to share my screen. Where's my screen share thingy now? Oh, okay, share screen. Okay, can you see The assignment, okay, I haven't fixed the dates yet, but I'll fix it soon. You are asked to advise a client who's looking into purchasing a cleaning company. There's 2 Sydney companies in mind, code name A and B. Excel spreadsheet, prospective XLS contain the data with the following 2 variables, and so on. So you need to do all kinds of calculations and answer questions. The client wants to know which company has the lower mean offers per crew. And then you need to do all kinds of calculations. So one of the things you need to do is compare the 2 using a regression analysis, simple linear regression. Now that we're only going to do next week. Well, you've done some of it already, but we're really only going to do it next week. So let me get that data up for you. It will be available tomorrow morning. I'll make it available tomorrow morning. As you can see, I still got to update the dates.
Cool.
Okay, so that's, can you not see my screen? Okay, so that's what the data looks like. And I'll bring the question back in here. Okay, so the problem is you need to decide which company are you going to recommend to your boss or to the client to buy. And the one company has got 5 crews and they clean 29 offices, and then they use 12 crews cleaning 54 and so on. And this is what company B did and how they clean offices. You guys want to take some time and read this? While I'm actually, no, I'll have to think carefully about it before just opening it up. So I want you to do descriptive analysis on the variables. Use Excel to draw a histogram for the number of rooms cleaned for each company. Use a pivot table to summarize the performance of the crews and so on. Then you need to add an additional variable where you divide the number of offices by the number of crews cleaned. Call this office per crew company, and it will look something like this. Which company has the lowest mean office per crew? Why does it want this? The other information suggests that company B might have higher mean. Test this hypothesis at a 5% significant level. Set out your analysis for this fully. What can be recommended to your client? Then you choose a client, and for that client, you do a simple linear regression and see if there's a relationship between the number of rooms cleaned and the number of crews. Justify the, and so on, state the interpretation and give a final summary. Nice assignment, huh?
It's like 3 of that mini exam quiz together.
Beg your pardon?
It's like that exam quiz that we do together, all 3 together, in a way.
Something like, well, it's in from each section in the book, if that makes sense. So this is the first couple of weeks, and this is the next couple of weeks, and this is the last couple of weeks. If that makes sense. Yeah. but it's all based on this data, and there's a sense in which this is a real life example. So the company really approached me and say, can you tell me which company should I buy? And they're cleaning offices. And you can see it's, yeah, okay. Okay, unless there's specific questions, I think we're done.
Okay, thank you.
You okay, Brenda? You okay, Charlotte?
Yes. This is all due on the 31st of this month.
Yeah, that's why I'll just have to sit and carefully work out the dates. I didn't want to on the fly now try and fix it. I'll have to go back to the course outline and look what's in the course outline.
Okay.
Okay, good night. Contact me anytime, and if you want to walk through your quiz exam too, or any other aspect, feel free to make a one-on-one appointment with me. Not while you write the exam, though.
Sure.
Hey, Sharma.
I'll just create a new document, different numbers, different wording, and just be like, I found this on the internet. Can you please help me?
Say again?
I'll just recreate it in a different word and different numbers, and then pretend that you can walk it through for me. Then I'll just copy and paste it.
Yeah. Yeah. In another course that I've given, and it's not true anymore, but the exams actually get published on the internet almost before the students write it with solutions. So we're now very careful on how we do this. And I always felt a bit disappointed that no student can figure that out, and I could figure that out. But that's just life. I'll check this one now. Maybe it is available on the internet, but then I'll change the numbers. So still okay.
Bye.
All the best.
Bye. Thank
God
you.
bless. Bye.
Bye.